how do we calculate these equilibrium constants? There's different ways. The most direct way is to measure the concentrations of the reactants and products at equilibrium. So we have here the same equation we've been talking about. H2 plus I2 making 2 high, right? And we're told that H2 is 0.11 molar, I2 is 0.11 molar, and high is 0.78 molar at equilibrium. This is at 445 degrees Celsius. Do we need the temperature to do the calculation? No. They're just specifying that because we're going to find Kc at this temperature, and it's not going to be true for any other temperature. So it's just kind of a fine print sort of thing. So to calculate Kc, we're first going to write the expression for it. You should always write the expression first. So products over reactants. So we have the molarity of high squared divided by the molarity of H2 times I2. Any questions about that? Then we're going to take these numbers that we were given and put them in. So high had 0.78, so 0.78 squared divided by the H2 concentration times the I2 concentration. Bless you. There is a common pitfall when doing expressions like this on your calculator, because we think of this as, well, that's 0.78 squared divided by 0.11 times 0.11. That's true, but if you tell your calculator that, it's going to give you 0.78 squared divided by 0.11 times 0.11, and that's not what we meant, right? So there's 3 ways, I'll tell you 2 of them, to avoid that. One is, well, those are brackets. Put parentheses on the outside of those guys and the times in the middle. So 0.78 squared divided by the quantity, 0.11 times 0.11. So that works really well. The other thing is to use that fraction button on your calculator. If you don't like fractions, that should be your new favorite button, because it'll let you type this in just the way it looks, and you don't have to worry about this dividing by a quantity business. Whoops. I'm getting lots of whoopses here. 50.28, and then there's some more digits. What would be a good number of sig figs? Well, we're doing multiplication and division, so 2. So we'll keep that guy. If we're gonna, be real persnickety. The good thing is we're not super picky about sig figs in Chem 1B. So if you wrote 50 without the decimal point, I don't care. Any questions? So that's the most direct way. It's not the simplest way, because you get this thing at equilibrium and we have to measure the concentrations of 3 different gases. That's a lot of work, practically speaking. Let's look at the same equation, same reaction, and we're going to start with different numbers of, different concentrations initially, and then we're going to see what the equilibrium concentrations are. So this is the one we just looked at. We were told that these were the equilibrium concentrations. This one happened to come from starting out with half molar this and half molar that, and none of that. When we plugged those numbers in, we got 50. That's what we did in the previous problem. If you start with half a mole of high, you're going to end up with 0.055 moles of H2, 0.055 moles of I2, and 0.39 moles of high. You plug these into the expression, you get the same number because the equilibrium constant is constant. Right? So we can try all these different combinations. It doesn't matter what we start with. If we wait for the reaction to come to equilibrium and we plug these concentrations into the expression, we're going to get the same equilibrium constant. Does that make sense? We can also calculate Kc if we know the initial concentrations and the equilibrium concentration of anything, just one thing. This is easier because knowing the initial concentrations, you don't really have to measure them. You can just make it that way. I put this much in, I know what it is. Then you only have to measure the concentration of one thing at equilibrium. So experimentally, this is easier. Calculation-wise, it's a little trickier. So it's helpful to use a table. So here we've got our reactant and our product. We're keeping it real simple here. And we're going to put in our initial concentrations. So we started with 1 mole per liter of A and none of B. Pretty common. Why would you put the product in there, right? And then when it comes to equilibrium, we measured the concentration of A and found out that it was 0.75 molar. We can figure out the rest. If this started at 1 and went to 0.75, how did it change? It went down by 0.25. Or it went down by X. So B starts at 0, it's going to increase. Here, X is the moles of A that disappeared. How's B going to change? We're going to get 2 moles of B for every 1 mole of A. So that's going to increase by 2X. So that's going to increase by 0.5. Is everybody okay with that? We've got different moles of gases now, but that's okay because we have 1 mole of gas making 2 moles of gas. The moles of gas are going to change. So then we take our initial and our change for the product, combine those, and we get final concentration at 0.50. Now we can calculate the equilibrium constant. The expression is B squared over A. We did our little table here, and we found that B is 0.5, and that's squared, divided by A, 0.75. Zero 0.33 repeating, we'll just call it 0.33. Any questions? What do these first letters spell? Ice. This is an ice table. You have now been formally introduced. We're going to be using a lot of ice tables in this class. So it's really important that you understand what I did in this table. Because if we don't understand this, it's not going to get easier. If we understand this, we can go on and we'll be okay. But if we're confused about this, we're going to have problems. So I'm going to try this. You have a thumb, right? So I'm gonna have you put your thumb up. You can hide your thumb from somebody else. It's as long as I just need to see your thumb. Thumb up means got it. Thumb to the side means kind of confused, kind of, sort of in the middle. Thumb down means totally lost. Okay, so got a good mix between got it and a little confused. So I think everybody's okay on, well, let's do it this way. Initially, yeah.
The x is just the number that's coming from the actual equation.
The x is coming from here.
Okay.
Yeah.
That's why I was confused.
Yeah. So we could say, well, this is going down by some amount.
Right.
We're going to call it x. So A, we're going to lose some, and we're going to gain B. And so B is going to change by plus 2x. This is the coefficient. That's why it's 2x. Does that help, sideways people? So, and I probably am supposed to start that way. I just don't remember. So put the changes in with respect to an x, and the reactant here was going down, so it's minus x. The product is going up, so it's plus. And then you look at the equation, and whatever the coefficients are, you put that in front of the x. Now, from this part, we can figure out what x is, right? 1 minus x is 0.75. So x must be 0.25. And so 2 times x is 0.5, 0.5 plus 0, and that's where we get the 0.5. Okay, let's do the thumbs again. Good, confused, totally lost. Okay, I think I converted at least all the people I can see. Good job. Okay, reaction between CO and H2 is carried out with these initial concentrations. It's boring to read them, so I'm not going to. Find the equilibrium constant. So here we have our chemical equation. What we want to do is we want to make an ICE table. Initial, change, equilibrium. Often it's convenient to just use the written equation as the header line for that. Oops. So here I'm going to have an initial and a change and an equilibrium, ICE. Well, let's just be thorough and put one over there. Let's just put one up here too, just to make it, I don't know, it's not pretty. We have initial concentrations. CH4 is 0.8087. So here I'm going to write 0.087. So that's an initial concentration. What do you think the initial concentrations of the reactants were? It doesn't say. Usually when we do a reaction, we just put in reactants, right? We don't put in reactants and products, because we're doing the reaction to make the products, right? We don't have them. So in a case like this where it says nothing about the product concentrations, we can assume that there wasn't any. So these are going to be 0. Is everybody okay with that? Yeah.
Is that the second problem or the first problem? You see there's 2 problems. The CO
one is it?
Oh,
It's listed twice.
so there's.
Oh, it's listed twice? Hang on. Okay, I see the confusion. So this is 16.6. It's supposed to be the first one, but it's the second one.
Yeah.
So I'm really confused. Let's just do this one because I already started writing on it, and then well, actually, I can look here. Yeah, I just, I skipped that. Okay, thank you. Thank you very much. I'm sure that was confusing for everyone. Thank you. Okay, so we okay with this?
Wait, why is it 0?
Why is it 0? They didn't tell us a concentration. Here's the arrow. These are the products. So, like, when you bake chocolate chip cookies, do you start out with some chocolate chip cookies? No, you only start out with the ingredients, right? And then you make the cookies, you produce the cookies. So typically what happens with a chemical reaction is we put put some reactants together, and they react, and they make the products, but we didn't have any products to start with, right? So if they're not telling you, it's going to be 0 for products. At equilibrium, H2 is 0.012. So we can write that in here, 0.012. And then we can figure out the rest of the table. So let's think about the change in terms of X. This one, is it going to go up or down? It's going to go down. It's a reactant. It's going to go down. And how many X's? 2X. It'll decrease by 2X.
Remember, second part of the page.
So this is the coefficient. Yeah, it's on the second part of the page. It's a different, yeah. Sorry. So sorry for that. How's this one going to change? It's going to go up, right? What's the coefficient here? 1. So that's going to increase by X. And what about this one? It's going to increase by 3X. Again, we're looking at the bottom of the page. Could we figure out what X is? Yeah, we can look at this one. So this is telling me that 0 plus 3X is equal to 0.012. So X is 0.004. You don't have to write that out. You can just do it on your calculator, do it in your head, I don't care. But this is how we figure that out. So here we're adding 3X to get this. Here, if we're adding 1X, one of these, to 0, what do we get? We get X, right? 0.004. Here, we're subtracting 2 of those. So we could write it like this, 0.087 minus 2 times 0.004. That's what we're doing. Oops, get the numbers right. So 0.079. Did I get that right? You guys have to check my math because I'm a mess. Now we can calculate the equilibrium constant. We should always write the expression. So here, K is equal to the products and the H2 has a coefficient of 3, so it has an exponent of 3. Divided by the reactants, that is a coefficient of 2, gets an exponent of 2. You should always write this out. And then you should always write out the numbers filled in. So we've got 0.004 times 0.012 cubed divided by 0.079. Oh, that's kind of ugly. Squared. My calculator is giving me a bunch of zeros. My kind of rule of thumb is if there's more than 3 zeros at the beginning of the number, it's good to put it in scientific notation. I'm going to put this in scientific notation. And 2 sig figs is probably good, so 1.1 times 10 to the minus 6. Yes, I realize that this one only has 1 sig fig. We don't care. Any questions? Okay, let's go back and do the first one. This one. Here we have 2 reactants and 1 product. We're given initial concentrations for the reactants and an equilibrium concentration for this. So we need to make an ice table. Later, you may be able to see all of this in your head, but for now, make the ice table. Things are going to get more complicated. Sometimes it's helpful to put a double line there because you can't see the arrow very well. I-C-E. A lot of students, oh, sorry. So in our ice table, we've got initial, change, and equilibrium. So they're telling us some initial concentrations. The CO was 0.27. The H2 is 0.49. They didn't say anything about the product. Again, I like to do the double line here. I didn't do that earlier because I forgot, because that helps me to see better where the arrow is. This is a product. They don't tell me anything about it, so I'm supposed to assume that there wasn't any to start with. They give me 1 equilibrium concentration, and that's this one right here. Now I'm going to put the change in terms of x's. So this went from 0 to something. It went up plus x. The coefficient is 1, so this is just 1x. This is a reactant. It's going down 2x. So minus 2x. This is also a reactant going down. Coefficient is 1, so it's going down negative x. Now, you write down as much as you need to get the correct answer down here. Without writing it down, you could do it like this. You could say 0.49 plus negative 2 times 0.11. Yeah, you might want to write over here, okay, x is 0.11. And then for this one, 0.27 minus x minus 0.11, 0.16. That's the hard part. A equals the products over the reactants. And the H2 is squared. 0.11 divided by 0.16 times 0.27 squared. Any questions? Yeah. How did I get 0.27? Great question. So I did the math just straight into the calculator without writing anything down. But if I wrote 9.4, we did that one first by accident. The end for today.